Good morning. In today's session, I'll be discussing about power transmission by circular shafts. So, the purpose of shafts is to transmit power. So, what will be the power transmitted by circular shafts and hollow shafts, hollow circular shafts? We'll see some numerical examples on this topic in today's session. Okay, so the basic equations to be remembered is the first one is the torsion equation, which is given as T by Ip equal to tau by R equal to C theta by L, where T is the torque applied, Ip is polar moment of inertia, tau is the shear stress at a distance r from the center of the shaft, and C is modulus of rigidity, theta is the angle of twist, and L is the length of the shaft. Okay. So for a solid circular shaft, the polar moment of inertia J is given as J or Ip. It is denoted by capital J or I suffix P. So which is given by pi d power 4 by 32 for solid shaft. This is for solid shaft. And for hollow shaft, it is pi by 32 into d power 4 minus d power 4, where d, capital D is external diameter and small d is internal diameter. J is equal to, this is for hollow shaft. Okay, and torque is given as pi by 16 tau dq, where this is obtained from this equation, torsion equation. T is equal to Ip into tau maximum by d by 2, or maximum distance, maximum fiber distance from the center of the axis, which is radius d by 2. Okay, so Ip is known, pi d power 4 by 32. So from which you will get pi d power 4 by 32 into 2 by d into tau. Okay. Tau means tau maximum. Okay, so that's how we will get here pi by 16 dq into tau, pi by 16 tau into dq. This is for solid shaft, and for hollow shaft, this divided by d by 2. Okay, so it becomes pi by 16 d power 4 minus small d power 4 by d into tau. Okay, into tau. This is for hollow shaft. The torque is equal to pi by 16 tau dq for solid shaft, pi by 16 tau into d power 4 minus small d power 4 by d, capital D, okay, for hollow shaft. And the power transmitted is equal to 2 pi n t by 60. Okay, 2 pi n t by 60, where n is the speed of the shaft in RPM. Okay, T is torque. So 2 pi n by 60 is nothing but angular displacement. Okay, so RPM, n is RPM, by 60 is RPS, revolutions per second, and one revolution is nothing but 2 pi radians. Okay, one complete revolution is nothing but 2 pi radians. For one revolution, the angular displacement will be 2 pi radians. So 2 pi n by 60 is angular speed. In other words, angular velocity, W. Okay, and this is in kilowatts, units of kilowatts, and horsepower units. We have to divide this by 75. Okay, in horsepower units, if you want to express the power, then it is given as 2 pi nt by 4500, 60 into 75. Okay, so with this formula in mind, we can proceed to solve some numerical examples. Okay, the first example reads like this: in a tensile test, a test piece of 25 mm diameter and 200 mm gauge length is stretched 0.0975 millimeters under a pull of 50 kilonewtons. Okay. In a torsion test, the same rod is twisted by 0.025 radians over a length of 200 mm when a torque of 400 kilonewton mm was applied. Evaluate the Poisson's ratio and the 3 elastic moduli for the material. Okay. So what is given is the tensile test results of a test piece of diameter 25 mm, length 200 mm. Okay, under the action of a pull of 50 kilonewtons. What is the extension? It is stretched by 0.0975 millimeters. Okay, and for the same test piece, the angle of twist is 0.025 radians under the action of torque. Action of the torque of 400 kilonewton millimeters. Again, over a length of 200 mm. Okay, over a length of 200 mm. First, by using these details, we find the Young's modulus. Okay, we find the Young's modulus. How will you get Young's modulus? Here we will find area, which is pi d square by 4. Okay, so it is pi into 25 square by 4. So it comes around 491 square millimeters. Okay. So once the area is known, we know Young's modulus is stress by strain. Stress by strain, which is P by A into L by delta L. Okay. P by L, P by A into L by delta. Okay, delta L is 0.90975 millimeters. Okay, so P is known, area is known, L is known, and delta L is known. So we can find Young's modulus. Okay, so what is the Young's modulus here? The stress is P by A is given as 101.83 Newton per mm square, that is P by A, and strain is delta L by L. Okay, so Young's modulus is 2.09 into 10 power 5 Newton per mm square. Okay, so Young's modulus is obtained. Now, from torsion equation, we will find rigidity modulus. Okay, because torque is given, diameter is known, so we can find moment of inertia, polar moment of inertia, which is pi d power 4 by 32. Okay, so it is coming like this. So T by IP, this is torsion equation, equal to C theta by L, and theta is given, L is known. Okay, so what is theta? So C is equal to, from this expression, TL by IP into theta. TL by IP, polar modulus into theta. theta value in radians, which is given directly in the problem. 0.025 radians it is given. So from this we calculate the rigidity modulus C, okay, which is coming out 8.341 into 10 power 4 mm. Sorry, the units are here Newton per mm square. Newton per mm square. Okay. Now, using the relation between this elastic moduli, we find the Poisson's ratio using the relation between E and C. Okay. E is equal to 2C into 1 plus 1 by m, where 1 by m is Poisson's ratio. Okay. So, 1 plus 1 by m is equal to E by 2C. Okay. This is 10 power 5. This is 10 power 4, not 104. Okay, 10 power 4. So, which comes out to be 1.253. And Poisson's ratio is 1 by m. So, 0.253. 1.253 minus 1. Okay. So, Poisson's ratio is 0.253. Poisson's ratio means ratio of lateral strain to longitudinal strain. Okay. Again, by using the relation between E and K, Young's modulus and bulk modulus, we find K value. Okay. We find K value, bulk modulus. Because here E is known and 1 by m we have calculated. Okay. So, we obtain the bulk modulus as 1.41 into 10 power 5 Newton per mm square. Newton per mm square. Okay. Yeah, that's how we solve this problem. Let us see one more example. A solid shaft, steel shaft, is to transmit a torque of 10 kilonewton meters. If the shearing stress is not to exceed 45 megapascals, find the minimum diameter of the shaft. Okay. So, the limiting condition is shear stress is not to exceed 45 megapascals, Newton per mm square. Okay. And it has to transmit 10 kilonewton meters torque. So, what will be the minimum diameter required for the shaft? Okay. So, for this, again we will use this condition. T is equal to pi by 16 d cube into tau. How will you get this? This is polar modulus, polar section modulus, which is IP by d by 2. IP by d by 2 r. Okay, radius of the shaft, which is from torsion equation. Okay. So, by using this condition, here the torque is 10 kilonewton meters. It is converted into Newton millimeters. Okay. So, we have to be careful while substituting in the formula. Okay. We have to use same units on either side. Okay. Here tau is in megapascals, Newton per mm square. So, we convert tau also into same units, Newton millimeters, and you will get diameter in millimeters. Okay, you will get diameter in millimeters. So, you will get 10 power 7 equal to 8.836 d cube. So, from which the diameter required is obtained as 104 millimeters. 104 millimeters. These problems are simple only. They are just like substitution of the given values in the formula. Okay, there is no complication as such. Okay, now let us go for next example. A hollow shaft of external and internal diameter of 80 mm and 50 mm is required to transmit a torque from one end to the other. What is the safe torque it can transmit if the allowable shear stress is 45 megapascals? Okay. What is the difference here between the previous and this one? Here torque is given for a solid shaft and diameter required we are defining. And in this case, the diameters for a hollow shaft are given, external and internal. And what will be the torque it can transmit? Okay. So the formula what we are going to use the same. Only thing is this polar modulus is given as pi by 32 into d power 4 minus d power 4 by capital. This is 16. Pi by 16 into capital D power 4 minus small d power 4 by capital D. This is IPR. So diameters are given, tau is given. What is the torque that it can transmit? Okay. So it is direct substitution in the form. Okay. Yes. This is the formula. Okay. Tau into pi by 16 capital D power 4 minus small d power 4 by d. Substituting the values, we will get the torque as 3.83 into 10 power 6 Newton millimeters, and but we express that in kilonewton meters. Okay, so it is 3.83 kilonewton meters. That is the torque the shaft can transmit. Okay, for the given data. Now, the next example. Okay, the example, this fourth example, it reads like this: a solid steel shaft has to transmit 100 kilowatts at 160 rpm, taking allowable shear stress as 70 megapascals. Find the suitable diameter of the shaft. The maximum torque transmitted in each revolution exceeds the mean by 20%. So the maximum torque exceeds the mean by 20%. So here the power transmitted is given 100 kilowatts and speed of the shaft is in RPM 160. And allowable stress is 70, shear stress, allowable stress is 70 megapascals, and maximum torque is 20% excess of mean torque. This T is mean torque, so maximum torque is 1.2 times of mean torque. Okay, this is the condition given. So now, if capital D is the diameter of shaft in millimeters, then use the relation P equal to 2 pi nt by 60, which gives torque. Okay, because power is given, speed is given, so we can find torque, that is in kilonewton meters, because this is in kilowatts. So convert that into Newton millimeter, 10 power 6 multiplied with 10 power 6. Okay. Now, maximum torque is given as 1.2 times of the mean torque. Okay. So 1.2 times of mean torque. Okay. And this torque is given by the equation T is equal to pi by 16 d cube tau. Okay, pi by 16 d cube tau. And tau is given here, maximum allowable shear stress 70 megapascals, and T is 7.14. This maximum torque we have to substitute here, and we can find diameter D, which is coming out to be 80 millimeters. Okay, the diameter of the shaft is 80 millimeters. Okay, so it is asked to find the diameter, isn't it? Find suitable diameter for the shaft which can transmit 100 kilowatts at 160 rpm with the stress not exceeding 70 megapascals. Okay. Yeah. Let us go for another example. Calculate the maximum torque that a shaft of 125 mm diameter can transmit if the maximum angle of twist is 1 degree in a length of 1.5 meters. Take C, the rigidity modulus, as 70 gigapascals. Okay, so gigapascals means into 1000 megapascals, 70,000 megapascals. That is Newton per mm square. So what is the length 1.5 meters and diameter 125 millimeters, and angle of twist is 1 degree in a length of 1.5 meters. So angle of twist is 1 degree, which is converted into radians, that is pi by 180. 1 degree is pi by 180 radians. Okay, and which pi by 180, keep it like that, and length is 1.5 meters, that is 1500 mm. 1500 mm. And C, modulus of rigidity, is 70 gigapascals or 70 into 10 cube megapascals. Megapascal is nothing but Newton per mm square. Newton per mm square. Okay. Now, how will you find? First, let us find modulus of moment of inertia, polar moment of inertia, pi d power 4 by 32. So here diameter of the shaft is 125 millimeters. So pi d power 4 by 32 is 24 into 10 power 6 units millimeter per 4. So as per the data given, we use this equation, torsion equation. T by J or IP. J also is represented as I suffix P, polar moment of inertia. T by J equal to C theta by L. C theta by L. So substituting the values, we will find the torque T. J is 24 into 10 power 6, C is 70,000, and theta. What is theta? In radians. We have to substitute theta in radians. Pi by 180 divided by L. That is 1500. Length of shaft is 1.5 meters or 1500 mm. So this is 0.814. The torque is 19.5 into 10 power 6 or something. You will get 19.5 into 10 power 6 Newton millimeters. So it is expressed in kilonewton meters as 19.5 kilonewton meters. Almost all the problems are like this. Most of the cases they are just like substituting the given values. Okay. Only thing is you need to remember the formula, the torsion equation, polar modulus. Okay. All this formula you need to remember. Another example, the last one. Find the maximum torque that can be safely applied to a shaft of 80 mm diameter. So diameter is given 80 millimeters. The permissible angle of twist is 1.5 degrees in a length of 5 meters. Permissible angle of twist is 1.5 degrees in a length of 5 meters. And shear stress is not to exceed 42 megapascals. So here angle of twist, permissible angle of twist is given and permissible shear stress is also given. Okay. So two conditions are given here. Both the conditions are to be satisfied. So first we will find out the torque using the condition, first condition. Okay. First let us see what is the data given here. The diameter of shaft is given as 80 mm. Angle of twist is 1.5 degrees. In radians, it is 0.0262. That means multiply with pi by 180. And length of shaft is 5 meters. Maximum shear stress 42 megapascals. So first we will find out the torque based on the condition of maximum angle of twist, and then by using the condition, second condition, maximum shear stress. So least of these two will be considered as the maximum torque that can be transmitted. Okay. First, use the condition of maximum shear stress. Okay, torque based on shear stress, maximum shear stress. Modulus of rigidity is it given in the problem 84 gigapascals. So what is the condition that we use for this? What is the formula we have to use? Yeah, T equal to pi by 16 tau into dq. Okay, this is T1. We are calling it as T1, torque based on maximum shear stress condition. Okay, that is pi by 16. Shear stress is 42 and diameter 80. So which comes out to be 4.22 into 10 power 6 Newton millimeters. Now the torque based on angle of twist. Torque based on angle of twist. Yeah, for that, first we will find out modulus polar moment of inertia pi d power 4 by 32. Okay, and substitute in this T2 by J. T2 means here the torque based on the maximum angle of twist. Condition of maximum angle of twist. So C is J is 4.02 into 10 power 6 and C is 84 into 10 cube Newton per mm square, and angle of twist 1.5 degrees, which is expressed in radians as 0.0262 and length in millimeters 5000. So T2 is 1.769 into 10 power 6 Newton millimeters. Okay. So of these two, the least will be taken as the maximum torque that can be applied. Okay. Because T1 is 4.22 into 10 power 6 and this is 1.769 into 10 power 6. The least is 1.769. So that will be the maximum torque that can be applied on the shaft. Okay. Yeah. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.